Okay, so I've taken the rotor off of the shaft to show you what I've done with the base electromagnet, or well, it's a toroid magnet with some wire wrapped around it, and it's connected to this coil through that bridge rectifier. This is a DC setup currently. I've got diodes between each coil. It's all DC straight up. And we're going to check that out in just a second. There it is. Oh no. So I gotta put that in there. That's funny.
Do you need a mallet?
Nope.
Okay.
Got it. Okay. Now, hopefully it'll be as lined up as it was before it popped out. That feels good. Heck yeah. Alright, so now it's floating on a magnet. It's hooked up with electricity wrap going around it. I was wondering if that electromagnet would be, if it would be more powerful with that going on. So I'm going to turn it on. So this system pulls about 4 amps altogether, 3.6. And as it goes through the system, the speed jacks up as the amps go down. But when the switch is stuck, like it was when it started, that read about 3.6 amps.
Okay.
So when it's perma closed, the amps stay. You got a reading on
45.
45?
46. 47. 48.
That's awesome. Yeah, I feel all kinds of steampunk with this stuff.
Mm-hmm. That's awesome.
So,
just those magnets in the middle there look
yeah.
like a Chinese star right now, flying through the air.
Yeah, in the center.
Mm-hmm.
Just that little part.
Yeah.
Heck yeah. I think the glasses go perfectly with the table. Like if you get a pan out and look at the little thing. Perfect, man. All right, we'll jack it up one more time.
There, you can kind of see it as it slows down. That is so cool.
Yeah, man, I just love how it starts off at 3.6 and works its way down by like 10 seconds to like 0.5 or 0.6.
Then it kind of turns into a blur after a minute. Wow, look at that.
There's a tiny bit of instability where the magnets are placed, I'm pretty sure. Like the spacing is a little off on like 2 or 3 of them. But it runs so smoothly up until that point, and then it just starts going, and you know, you gotta be, you can't just.
Okay.
Oh,
What is the name of the reed for your switch?
man.
Yeah, our eyes are not. Let me see if I can get a close up there. Looks like X. Here, move your
No, that's
move your thumb a little bit.
that says model.
SV.
CS1F.
Oh, the model. My bad. I was trying to read the brand upside down.
It's a high frequency reed switch, and it's awesome. It's totally awesome. You gotta, and it's kind of mechanical. I mean, you can flick it and it'll start working again. So that's kind of awesome. But it does get, it gets to the point where it starts sticking. So if you're running too many amps and you're using it and it sticks, so you're going to be pulling all those amps at once. So 3.2 amps right now.
Zero. Then it. Okay, I see. Then it kind of rotates down and goes all the way down.
Yeah, I'm happy that the reed switch can keep up with I call it the amp funnel. Just the way the coils are set up, it funnels down into a bottleneck, basically. In each stage, you get a burst of speed out of it. Yeah, that's going to keep on going. I don't think we're going to be able to see max speed with this rotor.
Right.
I think having the less powerful magnets is really helping with its ability to move faster. Because it doesn't get caught on the cores at all. Like, not even, and they're right up next to it. It's so awesome. Oh, yeah, I want to put this one on there because I know it'll run. At least on the 120s. Oh, heck yeah, man. 2 for the price of 1.
Bada boom.
All right, let's see.
This is a 3D printed rotor with very, very powerful magnets in them. Glued.
So 3.1. Oh man, it's not gonna. I mean, sometimes it'll do this. It won't,
And these are the struggles of a DIY champion.
Just doing it. Oh man, smooth, smooth, guys.
Yeah, when it's a solid red light, it's not good. It should be blinking at each magnet.
See, when it goes off, all the magnetic field just shuts down.
You can see that happening here.
I'm gonna try and catch the outer rim here.
Maybe start with a lower voltage here. I don't know if that would do anything.
No, that wouldn't work.
All right.
Maybe lower voltage from the transformer. But it's because of how big the magnets are that the reed switch is getting confused.
Okay.
When you move it up close,
There's more response.
it'll catch the space between the magnets. But yeah, this is ended up being more difficult than I anticipated.
All right.
Maybe a fresh one would work better. I don't know. Maybe we just put the other one back on.
Okay. Yeah.
Sounds like a plan to me. There we go.
It's too low.
Use the magnet smaller on either edge.
Look at this. Nice work, bro.
So there's more space between the tops of each magnets to apart more.
The reed switch is behaving that way because the magnets are so powerful. Yep.
Thank you. That's very true. But I mean, now that stator is backed out about an inch from the rotor, and it's still moving pretty graciously.
Nice.
There we go. We got pickup here. That's awesome. But yeah, so less powerful magnets if you want your stator close, and back it up a little ways, it'll still work pretty good if your magnets are more powerful. You got a reading on the
47, 48, 49, 50.
nice.
And let's look here.
But you got to remember, we're going through a transformer. It transforms about 100 volts.
Okay, right around 100 volts now. Yeah, I remember you calibrating that the other day. I can't. So I suggest you use Hall sensors like KY3 Hall sensor. Have you used one of those before?
Are they large? Are they have a wire sticking out the back? Or are they like for an Arduino?
Oh, the Arduinos.
Yeah. KY3, I'll check it out. Yeah, I have lots of trouble running the Hall effects like a switch, or I'd be doing it. And I don't. And this is without a transistor. But how would I be running the Hall effect? How would I be using it or applying it to the setup here? Would I be using a breadboard and transistors? These are tip 142s, are pretty good. Or would I be running it like that and it would catch the magnets like efficiently? Right? But it's like whenever I hook it up like a switch, it doesn't have any power going through it. Am I hooking it up wrong? Obviously. Obviously I'm not hooking it up right, but I do have a Hall effect sensor that I could hook up right now. Let me get it. Here it is. No, that's the battery. Huh. Maybe I'm not gonna find it right now. Keep my eyes out for it. I think that's running pretty smoothly. I mean, I know it took me a while to figure out that I was missing something, which was the elevation of the switch, to have it above those powerful magnets, just so it's catching the base, just the tip of the magnetic field there.
It's kind of hard to see, but there is a levitation bearing there with toroids. And then an induction coil wrapped around the fixed toroid on the bottom there.
Yeah, yep. And that circuit runs from, this is generating electricity here, and that's doing 75 volts of DC, which is going through this capacitor to the coil underneath, out the other side to the negative on the power distribution. So it's good. I mean, every other way I connected it, basically, except for one other way, I read 0 on the meter here.
Let's see what we got now. Yep, that's slowly going. Okay, it's finding its equilibrium.
So I think right about now, and we can turn this up. It's running so smoothly. I don't want to mess with it. We can turn it up, turn it up, turn it up. So 25 volts, and that's 0.1 or 100 milliamps currently. If it gets going any faster, it'll drop below that. Oh, it's going up. So it was at the top. So
Let me sneak around you.
25 in 0.2, 0.1.
So around 5 amps, or 5 watts.
So I've got A3144s. I think those are Hall effect sensors. They got the little Hall effects. I've got one nice size Hall effect sensor. I don't know where it is. I got 2 signal generators at the moment. Actually, I got like 3 or 4 of them. 2 of them are like little bite-sized ones like this. And then the other one's like right over there. All right, that's awesome. I mean, this, yeah, man.
Yeah.
I think it's only running basically the 120 coils. So that's this one, and that one. And these 2 aren't really factoring in as much as they were on the 12 magnet rotor. I mean, look at how far away it is. I'm thrilled by that. Because I know it'll be like, well, maybe not, because the magnets are so strong. Awesome. Thank you. Oaken. And this core I find is an accomplishment because that's iron filings and they're packed super tight. It's solid. And it helps out quite a bit. And then I've got 2 cores on the drive circuit, one right here. And then this one right here. And those are in the thicker end, I would call it. So those amps should be moving right along. The whole theory behind this is since this is where the electricity enters the coils, you got right here at 14 gauge, 90 turns, moving on to 18 gauge and 180 turns, moving on to 20 gauge. And it keeps on getting smaller and smaller and smaller, and it forces the amps to turn into speed. And by the time it gets here, the amps that you're registering are nowhere like, I mean, what you put in and what the cost is greatly reduced by having to funnel. What I'm saying, because when it sticks, it goes up to 3.6 amps. So that's what the circuit requires to function, 3.6 amps. And let's see here, 3.4 of those amps are being converted into speed by the way this is set up. But there's a coil inside of this coil. There's 3,333 turns of 32 gauge in the middle of this coil, and it's hooked up for AC. So the everything it goes DC, 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 AC, and with that AC pumping in the middle, you get a flux, like like a transformer flux. And that is applied to the drive circuit, which then goes to 26 gauge, which is 3,174 turns of 26 gauge with an iron core. And then we move on to the, the bottleneck, the actual cap. Here is 3,333 turns of 32 gauge wire is then connected to the switch. And then is connected to the ground. And voila. I mean, you get so much. I mean, it requires a lot. I'm not going to lie. I would probably have a different coil setup if I was going to do extremely inexpensive. I would have a lot more motion, a lot more strands. I've done it before. I've had it moving at like 0.18 of a volt.
Right.
No amps whatsoever. I mean, it was great.
That's awesome.
It was awesome. That's, but not like this. Not with the cores and everything in here. That won't work like this. Just having one core would screw that up. But if it was like an all air core, I could probably make it happen right now. Because to make that happen, you want to use one of these. Because if you use one of those, you got to have probably at least 3 volts in it to have it function right. But this one, it's fabulous.
Yeah, the homemade switches.
I think joule for joule, the homemade switches transfer the most power per switch, but they don't use, it's a very low frequency, so you're not going to get above 400, 500 RPMs. Kind of like this. It's going a little faster, I think, though. All right, I'll get a reading. We're going to have to go 9, divided by 9.
$6,400 divided by 9 would be 600 something. Hold on, 700 something.
700 something.
Mm-hmm.
So that's with the stator being an inch away. I think that's pretty good.
Mm-hmm.
And I mean the shaft is shaking a little bit. It's got a pretty good rhythm on it. So I'm just playing within my jurisdiction here. I gotta really put a lot of effort, and I need to make it like a chassis, like an enclosure, if I want to go really, really fast. I want to like start breaking 2K, 3K with something that size, man. You need to have like protective stuff, because this is by no means to spec. Like perfectly, I had to eyeball this. This is eyeballed, so I know it's not good, but it's good enough.
So how much? What here is homemade?
All of it. Bobbins are bought, but all the coils are, well, the 2 green bobbins are recycled from previously used copper, and
That there's one 3D printed coil there, or bobbin.
yep, there's 3D printed bobbins, though they tend to get really hot, like if they're being misused,
Mm-hmm.
and melt on you. They'll literally just, if you're using PLA. Okay, like the stands, I 3D printed the stands, I 3D printed the rotor. I bought all the magnets. I didn't make any of my own magnets. The shaft, it was off Amazon. It's got a high iron content in it, so it's very magnetic. Shaft is very magnetic. All right. The power distribution, I had to buy that. And it works out pretty well. The design is, pretty, getting those toroid magnets centered in the middle. It was actually really easy for me to do because I have pieces, discs that are 4 inches in diameter. I have a 1/4 inch hole in the middle, and you just boom, you connect the magnet to the disc, center it, drop it on there. But even with centering it like that, if you're even just like a fraction of an inch to either side, then you get a little wobble.
Yep.
It's not healthy sometimes. All right, about the same speed. I'll cut it back though. That's pretty awesome. I'm going to make a coil that will levitate on that aluminum plate. I might have to retrofit a plug to run it off of the electricity, but what I'm going to try and do is run it off of this pulse motor right here, and we're going to get the AC kicking, and we're going to see if we can't maybe bottle it up real quick and just turn it on with a switch. See if it'll, because it's got to be a jolt. And I may have made it done before around these poles, but it wasn't on a bobbin. They were like coils that I wrapped, and it was perfect. It was like 18 gauge wire, just like it is now, with no bobbin. Well, I don't know. I was probably trying to copy something I saw on YouTube at that point. Honestly. All right. So what's up, man?
I think we're good.
All right. Cool beans. Is there anything else I want to do real quick? Oh, magnetic sculpture. We got the bearings coming in and the new rods. And it's all going to fit in this hole right here. So we're going to have a 1/4 inch bearing with a 1/8 of an inch hole. And we're going to have to build a whole like base, or we can use the base that's in here to get the 1/8 of an inch holes to put them in, all the sticks.
Okay.
They're 300 millimeters in length.
Okay. The sticks.
Yeah, how much is that? Like this now?
Yep. 300 30 centimeters.
30 centimeters. So how much is that? This now?
It might be.
Okay. That'd be good because then we have more room to play with.
Probably half of that.
Okay, that's good. And so we'll get the bearings. We'll get because these are going to spin like beautifully.
Mm-hmm.
These are nice and round. They're flat. They're acrylic. They're clear. And, we can, if we look at it from the top, real quick, as I set this up, let's see here. Here. Okay. That's one layer. It goes like this. And then it'll be like that. And then this layer goes like this. It'll be like that.
Okay.
So there's going to be 6 pulls going around the centerpiece, which I haven't decided whether I'm going to make bi-level, the centerpiece. I do know that it's going to turn all these discs, and it's kind of like a helix, because then, you know, this one, which is started here, 1, 2, 3, 4, 5, 6, right?
Mm-hmm.
And then 3, 3. No, that's not right. Doesn't matter. You kind of get the idea, right? All right. Just leave it at that.
There's a video somewhere. We'll find it and link it.
Yeah, it's yep. It's got because, well, and it's vertical. So if you take this right here and how I laid it out, and you go like this, you stretch it out, you'll get what I'm saying. It's a vertical sculpture.
Yeah. Yeah.
But, you know, the pieces that will make it so aren't here right now. So if I confused anybody, I apologize. All right. I think that's pretty much all I wanted to break it down right now.
All right.
Just trying to think. Yeah, we're good. So, I mean, thank you, everybody, for participating. I really appreciate your input, and I'll check out those Hall Effect sensors. All right, so KY3, thank you very much. Peace out. Have a good day. Please subscribe, like, notification bell. Bye now.